Welcome to this new chapter on Introduction to Machine Learning. We shall start with machine learning development life cycle. We have the task, the data, modeling, error measurement, training and optimization, performance measurement, validating and testing, and corrective measures. Let's get straight away with the task. Now, a task here refers to the kind of problem we're trying to solve. So we could have a regression problem, a binary classification problem, a multi-class classification problem, a density estimation problem, a clustering problem, an anomaly detection problem, and a recommendation problem. Let's look at the regression problem. Suppose we have data gotten from a school's administration of 6 different students. So here we have the class R's of each of the students, the mark gotten during the quiz. That's suppose we have this final mark which comes at the end of a semester, and then we have a quiz which is done in the semester. So we have this class R's and quiz. So here for the first student we have 73 and 12. And this student had a final mark of 13.2. Then we could take another student, say this student, the fourth student, with a class R's of 57, quiz 8, and it should be noted that this class R's is on 90 hours. That is, each student is supposed to have done 90 hours to complete this semester. Then the quiz mark is on 20, while this final mark is on 20. So in this case, we have 57 class R's, 8 on 20 only in the quiz, and the final mark is 8. So having this kind of task or having this kind of problem to solve, we can identify that we could use regression model. Reason being that we have real inputs and real outputs. So these outputs could go from 0 to 20, this could go from 0 to 90, this could go from 0 to 20. Let's keep the status away for now. We're gonna use it in other tasks. Let's suppose that we go to the school's campus and we get more data. So we're not using only this 6-row data set, but now we have much more data to work with, and we obtain a plot which is like this. So here we have the class R's and the final mark. We've kept out this quiz column because it's going to make it less evident to visualize. So we just use the class R's only. Now, it's normal that the class R's and the final mark are actually highly correlated, because the more class R's you have, or the more classes you attain, actually, you should have a better mark. Now, with the linear regression model, or with basically this regression model, we are trying to look for this best fit line, or trying to look for a function which best represents this data. Now, we could add up the quiz and the class R's and have a 3-dimensional figure here, and actually do some analysis on how these two are related to the final mark. So what is to be taken off from this section, or from this subsection, is that you should be able to identify from your task the kind of model you will be working with. So generally, when you have this kind of problem, you should be thinking about working with a regression model. Now, let's see how this task, when modified, will lead to the usage of a different kind of model. Let's suppose now that any mark less than 10 is considered to be a fail, and any mark greater than 10 considered to be a pass. So we have 13.2 is translated to P, 9.5 to F, 17 to P, 8 to F, 11 to P, and 18 to P. So below 10 is F and greater than 10 is P. So in this case, we don't have exactly the same kind of problem to solve as before, wherein our outputs actually could take real values from 0 to 20. Here our outputs can only take two values, P and F. And since we're working with numerical data, generally P and F will represent 1 and 0. So in this case, if we go ahead and look at our data set this time around, we could modify this part. So yeah, we don't have the final mark again. We just have quiz and class R's. So we see that as the quiz, or as your mark increases in the quiz and the number of class R's increase, you tend to fall in this region, this orange region, which basically represents the students who passed. So here, unlike this plot where we had class R's and final mark, we have class R's and quiz, and the final mark is gotten by looking at the color simply. So yeah, this orange points represents the points where the final mark is P, and this white points, the points where the final mark is F. So yeah, represents the students who failed the final exam, and here the students who passed the final exam. So notice that our problem has actually changed. We are no more trying to find or predict the final mark, which was between 0 and 20, but now we're trying to say whether the student passed or failed, and hence the term classification, because here we're just simply trying to classify these two, say, classes of students, or these two categories of students, unlike here where we were trying to find the final mark of the student by some model or by some function. Now let's suppose that we don't only have two categories of students, but now three categories. So here we have P, F, and V. Basically, P represents students who have passed, but with marks below 17, and V represents students who have passed with marks from 17 to 20. That's why we have these 2 points with V's. So in this case, we're dealing with a multi-class classification problem, or a multi-class classification task, wherein we're trying to categorize or group our outputs into 2, or let's say into 3 or more different classes. So in this case, instead of having this kind of plot, we should have something like this, wherein we have our class R's quiz, and this green represents the top students, that's the very best of the best, and this is somehow the average students to also very good students, because 16 is a very good mark too. And then here we have the students who failed. So the aim of this section is to give you that intuition to be able to differentiate between a regression problem and a classification problem. Now, classification is not only used in this kind of situation. We could also have this when dealing with image data. Suppose we want to say whether this input is either a train, a dog, or a cat. So suppose we have these 3 different kind of objects. So here we have this dog, cat, and train. Now, when given an input, say a cat, we want to be able to say whether that's a cat, a dog, or a train. So when given a task, it's important to know whether we are dealing with a classification problem or not. Let's move on to the density estimation task. In density estimation, we're trying to represent compactly a data set like this one, for example, into or using a probability density function, which could be a normal probability density function, binomial, gamma, and many others. You could consult our probability course to have a deeper understanding of probability density functions. Now, once we've modeled our data in the form of a probability density function, when given new data or unseen data, we should be able to use our probability density function for inference. That is, to be able to infer and see what value exactly our output should have based on that probability density function. Generally, probability density functions have certain parameters, and it's these parameters that during training we'll be trying to get, such that when given an input, or say when given this x, given x previous, we should be able to use or make use of the trained parameters to infer and get the output. It should be noted that when the data gets very large, this kind of models or this kind of systems find it difficult in modeling the data. Let's move to clustering. Clustering is an unsupervised machine learning technique which basically uses only the inputs to segment the data and bring out certain relationships existing in the dataset which we may not have seen very easily. This is highly used in customer segmentation and many other applications. So taking this example from this data, we may have a situation where you're trying to provide home class services to some students who may need help, or some extra class for some students who maybe haven't attended many of the normal classes. So with this input and with a clustering algorithm, you should be able to segment the student population into students who need extra classes and other students who do not need extra classes, and the students who need extra classes are going to be a target. Now let's move on to anomaly detection. As the word goes, anomaly detection or anomaly has to do with any data points or data points which are actually far from the other data points. So in this case, we should be able to flag some inputs as unusual, and based on this take certain decisions. So this is why this kind of algorithms are greatly used in security systems. Now let's look at this example. Suppose we are used to having a certain number of students, or students with high class R's having very high final marks, and then the student comes up with, say, a number of class R's of 2. That's the students has attended only 2 hours out of the 90 hours, and that student scores 20 in the quiz and 20 in the final exam. So this kind of student is going to be under some investigation, because it's quite unusual to have a situation where a student has few class R's and scores very high marks. In recommendation systems, we make use of previous data, say, of a user in a platform like, for example, YouTube, to be able to recommend other services to the user. So suppose you're used to watching a certain kind of videos, or let's say you're used to watching videos on programming. You obviously have, say, some ad which is going to pop up telling you about some course which has to do with programming. The aim of this section was to make you understand exactly which kind of model or which kind of algorithm you shall be using depending on the task you have at hand. So whenever you have an idea or whenever a problem comes up, you should be able to know whether it's any of this. And it's important to note that this list isn't exhaustive, as there are many other tasks that exist. And also, as we go through the course, we should select any of these tasks, or maybe 2 or 3 of the tasks, depending on the kind of problem we have at hand. In our next section, we shall be dealing with the data. We shall be seeing how to better use this data we are given, say, this kind of data or this image data or some textual data, to come up with very efficient systems which make great use of this data.